When studying definite integrals, some of them are going to be quite challenging to evaluate, and in practice, in both science and economics, it's useful sometimes to be able to at least bound and say this integral is no larger than some other quantity or no smaller than some other quantity. We're going to take a look at a simple example of that here. Consider the function f of x equals 5 sine of 2 pi x. We remember from our earlier studies what these various scaling factors do. The 5 is the amplitude, and the 2 pi tells us that the period of this function will be 2 pi over the scaling factor, and so the period of this sine function is going to be simply 1. All right. Now, that means we can sketch it fairly easily. We'll make this whole interval here 1. I'm only going to sketch the positive x values because we look later on the integral we're interested in is only from 0 to 1/2. There's no negative values there. So if we sketch this out here as our x and our graph, here we go. What we're interested in looking at is an argument proving that the statement 0 is less than this integral is less than 5/2. Well, let's get a graphical interpretation of that integral. It's that area there in green. So how could we make a statement about that relative to these other two numbers? I think everyone is pretty easily convinced that this integral is definitely above the x-axis, so it's positive, and so it's bigger than 0. The argument about the 5/2 might seem a little more surprising. However, if you remember where this amplitude is, we're guaranteed that everywhere on the interval from 0 to 1/2, on that interval, we have our function is going to be less than or equal to 5. And so what we can say is on that interval, the area underneath the graph y equals 5, shading this whole thing in here, that area under the graph of 5 is going to also have to be larger than or equal to, we can see it's less than, but potentially less than or equal to the area under the graph. And what is that equal to? That's equal to the integral of 5 sine of 2 pi x from 0 to 1/2. So the fact that the curved function, is bounded above by the straight line 5 means that this integral is going to be less than or equal to this integral. But what's this value here? What's the integral of 5 between 0 and 1/2? We're going to learn specific techniques later on, but if we just look at this graph or this diagram, it's a rectangle with height 5 on this side, 1/2 on the other, and so the area is 5/2, 5 times 1/2. So the area underneath the green, under the curve here that's represented in green, is going to be less than the area represented by this rectangle, and so we'll get a relationship between the integral and this nice simple value. And it comes from the fact that our function is never exceeding the value 5, so the integral will never be exceeded by the integral on the same x range of the simple function 5, which comes out to a rectangular calculation. In general, we can make that same statement with a little more formal nature here. If our function, here's what we did before, if our function is less than or equal to some m value, then the area under the graph is going to be smaller than the area of some rectangle, which is m by b minus a. So again, the length of the interval and then the highest height we reach. And we can do the same thing on the bottom side. If we know that our function is always bigger than, say, 0, then our integral area is going to be always bigger than the area underneath the graph of the simple lower bound. It's worth noting that these are pretty crude. In fact, what we're doing is some variation on a one interval left or right hand or midpoint rule. So it's It's occasionally handy, but it doesn't give you a very precise range in most cases. If your interval's long, then this is going to be a pretty broad inequality. Sometimes we can get lucky though, just in that same example. If we change the limits of integration to be 0 to 1, can we get a better bound? Well, I think we can, because we just looked at that graph. We said that was 1 here. Well, if that's the graph we're looking at, I think we can all be pretty well convinced by the symmetry of the sine graph that these area above and below the x-axis are equal. And what does that mean about the overall integral? It tells us that the integral value overall is going to equal 0, because we get perfect cancellation between the positive contributions above the axis and the negative contributions below the axis. So here we could limit it to be between 0 and 5, or actually be negative 5 and 5, but we can get more precise because we have some nice symmetry in our problem. Another thing that we often do is not compare integrals to constants, but integrals to each other. So let's take a look at this scenario here. Two cars start at the same time from the same starting point, and we're going to be given velocities, and guess what? We're going to be looking for distances in a second. So if we look at this graph here, the first car moves at velocity v1, which is t, so a nice straight line there. That will be v1, and our axes here are t and v, and we're doing this over the first second, so let's take a look at the second car moving at velocity v2. Let's go here. So it always starts off flat, it's a parabola, and then it would do something like this. And we know when t is 1, I get 1. When t squared is 1, we get 1. So those two graphs intersect at t equals 1. So that would be a sketch of these two velocities. The question that follows up is which car travels further? So we're talking distance here in the first second. Relate this to a definite integral. Let's go back one step. I think we can easily convince ourselves that the area underneath the green here is going to be smaller than the area underneath the blue line. And what does that tell us? Well, we've already talked about velocity time graphs. The area underneath it represents the distance traveled. And so the distance traveled by car 2 is going to be less than the distance traveled by car 1. And that might phase some people thinking that t squared is smaller. Just remember, we're looking at the interval 0, 1, so it's not later on. Absolutely, when t gets to 2 and 3 and 4, t squared is definitely larger than t. But on 0, 1, t squared is actually smaller. What kind of relationship are we finding here? What are we basing this on? What we're really basing this on is that v1 is always, let's go the same order here, v2. If our speeds are always in that relationship, that one is always less than or equal to the other, then we have to have the areas related in the same way. And this is on some interval AB, and we will have that same relationship for their integrals just because of the area argument. If this one's always above that, then I'm capturing more area, and so the area underneath that must be larger than the area under v2. And here it is more generally, if we have two functions, one smaller than the other on the interval, then we get this relationship between their integral values. If the function's bigger, its integral would be bigger as long as the interval is the same.